And we're back, continuing our graphing with the calculator and doing our big procedure. Now I went ahead and graphed with the calculator e to the negative x squared so I could see what it looks like. It doesn't really look like it does too much. There he is. Looks like he's kind of, if I were graphing this one, I probably would zoom in on this little area here. I would use a little bit of calculus to see if it does anything in these endpoints, or is this going to be the only place where it has any sort of maximums or minimums. First up, identify the domain. Number one, whoops, need a pencil. Number one, the domain of this thing doesn't appear to have any restrictions. Looks like I can put anything in there from negative infinity to positive infinity. So I'm going to say the domain is negative infinity to positive infinity. I can put anything in there. Symmetry, normally I'll look at this at the end, but I can see that I have an x squared in here, and I believe that it'll have even symmetry. I can look at this graph here and say, yeah, I see that it's kind of the same on either side. It probably is this even symmetry. First and second derivatives are, and I need to go ahead and get those. So f prime of x and f double prime of x. And I'll do that algebra and be right back. Alright, I did my derivative work. Now I need to see where these two things can equal 0 or fail to exist. The first one, relatively straightforward, that can't be 0, so x equals 0 is critical point. Here are my possible inflection points. They would be, looks like just this thing can be 0, so I can move the 1 over, divide by 2, and take square root of both sides. X equals plus minus, looks like square root of 1/2, and this can be written as plus minus 1 over the square root of 2. Could also be written as square root of 2 over 2, but whatever. Those are my possible inflection points. Now I'm going to do my number line, and I need to check on either side of all of these different points. And these are the points that I chose on either side, and when I plugged in a -1 I found that it was positive, so that means my function is increasing when it's less than 0 and decreasing when it is greater than 0. That means that x equals 0 is a local max. And it also means, seeing as I have exactly 1, if you'll remember that 4.13 I think it is. Anyway, if you have exactly 1 critical point, then that point is also an absolute. So, and absolute max. And we did that in section 4.2. Then, since here at this, now 1 over square root of 2 is 0.707, so this negative, I tested it -1, so this one would be concave up. This section would be concave down, since it's less than 0, and this section would be concave up. And that kind of fits with my picture, and I see that I really have found all those different extrema. I also need to get any x-intercepts, see if it crosses over there. So I test to see if I can get a point where, you know, y is 0. So I'll take the natural log of both sides. And what is the natural? Oh, I can't take the natural log of 0. So it doesn't ever cross, so no intercepts. I'll say no x-intercepts. Clearly I have a y-intercept up here at the top, so if I plug in a 0 for x, my y-intercept is y equal 1. E to the 0 is 1. I've done the extreme values inflection points. Let's see, both of these are inflection points because it changes from concave up to concave down. So I'll scratch out possible and write it. These are the inflection points. Let's do the horizontal isotopes limit as x goes to infinity of e to the minus x squared. As x gets larger and larger, we're going to find that this gets, as x gets larger and larger, this gets closer and closer to, with this e to the x, so then this thing gets closer to infinity, and then that just gets closer and closer to 0. And same thing when I plug in a negative infinity. And I look and notice that that is what my graph is showing here. All of these things, all this pertinent information was in this grid, but I'm verifying that with my calculus. And so I probably wouldn't pick this graphing window. I see that everything happens in this tiny little window, so I'm going to pick that tiny little window. I'm going to and show you what this looks like. An appropriate viewing window. I don't know why I just wrote a 0. An appropriate viewing window might be, let's make it go to, how about, we'll make on the x-axis, let's go to negative 5, 5, counting by ones. And then on the y, let's go up to 2. And I really don't need to go down to negative 2, I could just go down to 1, but a y scale is going to be a 1 and you're a 1. Alright, and I'm going to give you that graph. Well, there it is. I'm not really crazy about it. I think I'm going to reduce that y scale some. I think I'm going to make the y go up to 2 and then just down to 1. See how that looks a little better. Ah yes, now this is stunning, isn't it? I really like this. I'm pretty happy with those results. And what I did was I chose the y instead went to, oops. Okay, the x went from the negative 2 to 2, and the y I did from, okay, and I like this. This looks really nice. Okay, next one. Alright, I graphed this on my TI-84. This was what I got. I don't know if it's, you know, in that other graph that we had some things that happened over in here. I don't know if this thing keeps on going up in both directions or if there's some stuff lurking over here somewhere that I can't see. And how I'll know for sure as I go through my little calculus. So let's look at the domain. Number 1, the domain looks like I can have any x, so there should be values for this. So domain, negative infinity to positive infinity. The symmetry, nothing that I can see, and I look at this graph and it doesn't look like it seems to have any symmetry. So far I'm going to just say none. I'll see when I get finished. Now I need to take the derivative, and once again this is going to be another messy one, so I'll give you a break and I'll do that part and then come back. Okay, here's a mess. I found the first derivative, went through and found out where the critical points were. I then took the second derivative and actually used this one right here when I took the second derivative. I kind of liked it better using the product rule there. Went down through, and this was what I ended up with. I had to check to see where the second derivative equaled 0. I saw that this didn't factor, so then I had to use the quadratic formula. Plugged it into the quadratic formula, found out that this second term here is greater than 100, which means that you will get a negative underneath the square root, meaning that you had imaginary roots, so we don't have any places there in our that would give us real roots, except for at 0 where the second derivative fails to exist. Now what I'm going to do is create my number line and test my points on either side of that, and I will give you that monstrosity as soon as I get it completed. Alright, my number line with my critical points on it, and I tested to see whether or not the first derivative was positive or negative at these particular points. -1 over here was less than, so that meant it is decreasing, then increasing, then at a half it was decreasing again, and then after that it is increasing. I note that I have two local minimums. Local min at x equal -4/9 and at x equal 1. Local max at x equal 0. Both of these were concave up, usual kind of function. And let's see, next identify extreme values and inflection points. No inflection points. No inflection points. I need to get what these values are, so I need to get what the actual point is at -4/9, and then I'm going to get that y value, and then at 1, and I'll get that y value, plug that in right here, so I'll have those 2 points, and then I'll also get this point as well. I'll have to go back to my original function and plug that in. Now I also need to find those x-intercepts. I'm going to go ahead and let my calculator do this for me, and I'll put those snips up here for you. Here's a sample of what I did to get one of the zeros. Now of course this is getting approximate values for my zeros or for my intercepts, but I hit, on mine it is the blue second button, and then I hit calc, and I scroll down to the 0, and of course any of those values that we had to calculate for all of these, I use that as well. So when I wanted to calculate the value of x equal -4/9, I just plug that into value and it spits these answers out for me, and I don't have to do the computation. So this is me going to the left side of that 0, then to the right side of the 0. I don't worry about the guessing, but you can move it closer if you want to guess. Just be sure you're on either side of that x-axis, you know, the left and then the right side of that axis, and it will give you that approximate decimal answer that you need for your zeros. And there are 3 zeros for this function. There's one here. I already know that one, that's the 0.00, and then there was another one there that I would need to go and get. I probably would zoom in on this graph and get a better graph, so I'm going to go ahead and do that and show you a graph that I would be happy with if it were my problem. Alright, note with this new graph I can tell that I'm really, you know, this 0 here isn't at -1, it's a little bit over to the right some, and this graph kind of makes it look like it's crossing there at 2, but if I have zoomed up on it enough, I see that it is not quite. Also, I can note this weird thing that's going on here at 0, because it is a weird little cusp or corner point that's going on. Anyway, this concludes section 4.3. See you at the Collaborate.